Welcome to the second session on electrolytic conductance. In this session, we will be seeing variation of conductances with dilution. Before going to variation of conductances, we will just recall the variation of conductances with respect to specific conductance and also molar and equivalent conductances. As you all know, specific conductance is the conductance of a solution whose volume is only 1 cc. So, if you take a solution, in that electrolytic solution, if I measure the conductance of 1 cc, that becomes the specific conductance, or you just call it as conductivity. In the other case, you can either take the equivalent conductance or molar conductance. Equivalent conductance is the conductance of a solution containing 1 gram equivalent, and in the case of molar conductance, it is the volume of the solution, whole volume of the solution containing 1 gram mole. So, just refresh this, we will go for the variation of specific conductance with conductivity dilution first. So, here we know that if you take an electrolyte solution, so this is an electrolyte solution, okay. Of this whole solution, if I am going to take the conductance of only 1 cc, suppose this is 1 cc, 1 centimeter cube of a solution. If I take the conductance of 1 cc, it becomes specific conductance. Okay. Now, this is the case when I have taken an electrolytic solution. Now, what I am going to do is, I am going to dilute it, and let us see what happens to the conductance when it is being diluted. So, this is a condition in the undiluted form. Next, I am going to take the same solution in a larger volume where it has been diluted. So, the volume increases, but we do not add the electrolyte. Actually, this is an electrolyte taken in a vessel to which we have added more of solvent and diluted, so that the electrolyte occupies the same quantity of electrolyte is occupying the larger area. Now, what happens here is, so what happens to the ions in the electrolyte? They move far apart, they will not be closer. So, number of ions contained in 1 cc. So, in this case, it is more closer where the solution is concentrated, but when we go for a dilute solution and you take 1 cc, that will be having fewer number of ions in it, or you can say that number of ions per cc decreases as we increase the dilution. When we increase the dilution, number of ions per cc is decreasing, and we know that conductance depends upon number of ions, and since number of ions are decreasing, what will happen to specific conductance or conductivity? It decreases. So, specific conductance or conductivity, whatever you call it, decreases with increase of dilution. So, here the reason for that is number of ions per cc decreases as we go on diluting the solution. Okay. Now, let us see what happens to molar conductance or equivalent conductance. Molar conductance or equivalent conductance is the conductance of 1 gram mole of an electrolyte containing solution or 1 gram equivalent of an electrolyte. So, here suppose we take a solution which contains 1 gram equivalent or 1 gram mole, make it as mole, 1 gram mole, or it can also be equivalent, both will be similar. The only difference is, in one case I will be taking gram mole, the other case it is 1 gram equivalent. Now, I am taking this in some 100 ml, let it be 100 ml. Okay. Now, what I am going to do is, I am going to dilute this solution too. So, I am going to dilute it and I am going to convert the volume into 1000 ml. So, I have diluted it 10 times. Okay. So, again here you have not added any amount of solute or electrolyte. Here you are having again 1 gram mole or 1 gram equivalent, whatever it is. It is again occupying a volume of 1000 ml. Here the volume has been increased. Now, in this case, what happens to the molar conductance or equivalent conductance? Actually, what happens is the molar conductance or equivalent conductance increases with dilution, not over, it increases with dilution, okay, and reaches a maximum value. Reaches a maximum value. So, why is this so? See, we know that here 1 gram mole of an electrolyte was first occupying a volume of 100 ml. So, you can see that all the ions are closer together. Now, when it is occupying a volume of 1000 ml, the ions will be moving apart, okay, and they will be occupying more volume. Okay. So, what are the factors that will be depending on the variation of conductance with dilution? There are two factors. One is number of ions, and second factor is interionic attractions. These are the two factors which determine the conductance of an electrolyte. So, here we know that we have two types of electrolytes, we have strong as well as weak electrolyte. So, you can't explain it just taking both together, we will differentiate them. Weak electrolytes we will give another explanation, for strong electrolytes we have to give another explanation because their behavior are different. Now, when we come for the weak electrolyte, now let us take the case of a weak electrolyte. Weak electrolytes actually they do not ionize completely in a solution, they are only partially ionized. So, when a weak electrolyte occupies 100 ml of a solvent or a solution, you will have a certain amount of weak electrolyte dissociated. When the volume has been increased to 1000 ml, it changes because more and more of solvent is added and more of electrolyte gets dissociated. So, in the case of weak electrolyte, that is one point. Another point is, as the solution gets diluted, there will be the ions will be moving apart, the interionic attraction will be reduced. Okay. Now, the movement of the ion is the reason why it carries current. When the movement of ions are faster, you can carry more current. If it is slower, it can carry only a small amount of current. So, what we are going to do here is, when we dilute a solution, there are two possibilities for a weak electrolyte. One is the degree of ionization, or you can say that the ionization of the electrolyte is keeping on increasing, while in the case when the solution is getting dilute, the ions are also moving apart. So, there will be a decrease in interionic attractions. Now, what happens if interionic attraction is there? Actually, an ion which is positively charged, suppose, that will be always attracted by negative ions. So, when this positive ion tries to move, the negative ions pulls it back because they are oppositely charged. When these ions they get far away from each other, these attractions are reduced. So, that is one factor which helps the ion to move faster, that is, when we dilute a solution, the ions move apart and therefore, the interionic attraction is reduced. and the ion moves with a certain velocity. And therefore, the two factors which helps to increase the conductance with dilution. In the case of a weak electrolyte is when more solvent is added, the ionization increases. Ionization increase means there is an increase in ions. Besides, as the ions move apart, the interionic attraction is decreased, and therefore, again ions can carry more current. So, these are the two factors which help to increase the conductance when we go on diluting. So, in the case of a weak electrolyte, there are two factors. One is number of ions increasing with dilution. Second factor is decrease in interionic attraction. So, these are the two factors which are responsible for increase in molar or equivalent conductance in the case of a weak electrolyte. So, you can see now let us go for the graph. This is a plot of conductance. It can be either considered as molar conductance or equivalent conductance, both vary in a similar way. So, here it is the molar conductance. For a weak electrolyte at the beginning you can see the value of conductance is very low. It keeps on increasing, and after a certain period you can see there is an abrupt increase and it goes almost parallel to the molar conductance axis. There is an abrupt increase, and that is a case where the interionic attractions are very much reduced and whole of the electrolyte is completely ionized, and therefore, it shows an abrupt increase. So, these are the two factors where a weak electrolyte dilution happens, resulting in these two factors and increases the molar conductance. Now, let us take the case of a strong electrolyte. Strong electrolytes, as you all know, the two factors are number of ions, that is the first factor we were saying about. So, in the case of a strong electrolyte, you can't say that number of ions are increasing. Why? Because strong electrolytes, you can say, so for example, if I take sodium chloride, in the crystal form itself it is existing as sodium ions and chloride ions. So, when we dissolve in water, it is already as sodium and chloride ions, but still. So, you can't say number of ions are increasing, it is not the case. So, what should be the reason why molar conductance or equivalent conductance is increasing for a strong electrolyte? So, number of ions are not increasing in the case of a strong electrolyte. In the case of dilution, what happens is, in a strong electrolyte you can say that a positively charged ion surely will be surrounded by negatively charged ions. So, what happens is there will be strong interionic attraction in concentrated solutions. Once the solution is becoming dilute, the ions move far away, and therefore, the interionic attraction decreases and there is an increase in molar conductance. So, when interionic attractions are decreased, only then ions will be free to move to carry the current. So, in the case of strong electrolyte, the only factor that determines the increase in molar conductance due to dilution is decrease in interionic attraction. So, with the decrease in interionic attraction, it goes on increasing, and therefore, you can see for a strong electrolyte there is a regular increase, and finally, you can say that this value can be extrapolated to 0 concentration, and the value is known as lambda 0, or it is a molar conductance or equivalent conductance at infinite dilution. It is named as molar conductance or at infinite dilution or at 0 concentration. 0 concentration, we can never take a solution to that concentration. You can keep on diluting and measure the values, and finally, you extrapolate the graph or the straight line to the 0 concentration level, and you get the lambda 0 values. And this can be determined only in the case of a strong electrolyte. In the case of a weak electrolyte, you can see that it goes almost parallel to the molar conductance axis, and in that case you can never find out the value of lambda 0 for a weak electrolyte. Okay. So, let us see what are the observations from the graph. Molar conductance of both strong and weak electrolytes increases with increase in dilution, that is for sure. Now, at higher dilutions, the rate of increase of lambda m, that is the molar conductance, is more rapid in the case of a weak electrolyte than in a strong electrolyte. Because we know that for weak electrolytes we have two factors, while in the case of strong electrolytes we have only one factor, that is decrease in interionic attraction. For a strong electrolyte, the molar conductance reaches a limiting value at a very low concentration, which is measurable, but in the case of a weak electrolyte, it fails to give the limiting measurable value. Okay. Now, the limiting value of molar conductance or equivalent conductance in very dilute solution, that is, we expect the concentration to be 0, because after that whatever amount of solvent you add, there will not be increase in molar conductance or equivalent conductance, and this value is known as the molar conductance or equivalent conductance at infinite dilution, which is denoted as lambda 0 m, and in some cases it is also known as lambda infinity m or lambda 0 EQ stands for, that is when we are taking the equivalent masses, or lambda infinity EQ. So, that is the case when dilution takes place for an electrolyte, the specific conductance, that is conductance per cc, decreases, while in the case of molar or equivalent conductance on dilution it keeps on increasing and reaches a maximum value for that, that is known as a limiting value, or it is known as at infinite dilution. Now, the increase in molar conductance or equivalent conductance depends upon two factors, that is number of ions and velocity of the ions, and this velocity of the ions, as you all know, it depends upon interionic attraction. As interionic attraction increases, the velocity of the ion decreases, because they will not be free to carry the current, because they are tied up with the interionic attractions. Once the interionic attractions are decreased, they are free to move and they carry current. Now, effect of dilution on a strong electrolyte and a weak electrolyte. Weak electrolytes, as you all know, it is a partially ionized one, and in the case of strong electrolyte, they are completely ionized. Okay. The number of ions increases and reduce the interionic attraction, and so the velocity of the ion increases in the case of a weak electrolyte. Number of ions are increasing, interionic attractions are reduced, and therefore, the velocity of the ions increases, and therefore, it keeps on increasing. While in the case of a strong electrolyte, there is only one factor, that is the interionic attraction decreases, and so the velocity of the ions increases. Now, in the case of a weak electrolyte, the extrapolation of the plot of lambda m against root c, root of c means root of concentration, gives a curve from which lambda 0 m can be calculated or cannot be got by extrapolation. So, weak electrolytes, it goes parallel to the lambda axis. In the case of a strong electrolyte, you can obtain the lambda 0 m value by plotting the curve and extrapolating to 0 concentration. In the case of a weak electrolyte, it is impossible, because as you have seen before, that is, the curve goes parallel to lambda m axis. Next, we will see what do you mean by degree of dissociation or ionization. Degree of dissociation of an electrolyte in a solution at a given concentration, you can take at any concentration C. Okay. This is defined as fraction of total number of moles of the electrolyte that has dissociated in the solution into ions. I will make it clear. Suppose you are having 10 moles dissociated at a particular concentration, 10 moles are dissociated at a, let it be some other concentration. Okay. Now, there is a weak electrolyte. So, at a particular concentration, let it be C, at concentration C, it is having 10 moles dissociated. But in total, if we are having total number of ions is 50, suppose, total number of ions that can be obtained from that electrolyte, suppose it is 50. Then degree of dissociation alpha means, after that 10 moles are dissociated, 40 moles undissociated. So, alpha means, that is, out of 50 you are having total number of moles 50, out of that only 10 moles are dissociated, and this fraction is known as alpha, that is, it is the fraction of total number of moles of the electrolyte that has been dissociated in solution. So, one more factor we know that, suppose number of moles dissociated, let that be put it as x, number of moles dissociated, and if total number of moles is y, this is dissociated. Okay. And if y is total number of ions. Okay. Now, in this case, I am measuring the molar conductance at a particular concentration C. At a particular concentration C means, at concentration C, x is the number of moles of electrolyte that has been dissociated, and therefore, lambda m will be proportional to this number of ions dissociated at that concentration. Now, when lambda m is at infinite dilution, that means limiting value where all the ions are dissociated, means that means lambda 0 m can be taken as proportional to total number of ions. Okay. So, lambda m means that is number of ions that has been dissociated at that concentration, and lambda 0 m is proportional to total number of ions, that is when all the electrolyte has been completely ionized, and therefore, the degree of dissociation alpha of a weak electrolyte is equal to lambda m by lambda 0 m, because lambda m corresponds to the number of ions that has been dissociated, and lambda 0 m corresponds to the total number of ions that is present in that electrolyte. So, alpha can be determined by taking the ratio of lambda m to lambda 0 m. But in the case of a strong electrolyte, this is a case when we consider a weak electrolyte. In the case of a strong electrolyte, as they are completely ionized in solution, you can't say that alpha is equal to lambda m by lambda 0 m, because in that case lambda m is not proportional to number of ions that has been dissociated. Lambda m stands for the conductance at that particular concentration, and lambda 0 m the conductance at infinite dilutions. You can't say it is proportional to number of ions present in the solution, and therefore, for a strong electrolyte, it is considered as a conductance ratio, simply a ratio of conductances, but not equal to alpha for a strong electrolyte. So, now in this session we have been seeing variation of specific and molar conductances with dilution. We know that specific conductance decreases with dilution, while in the case of molar conductance it increases and reaches a maximum value known as molar conductance at infinite dilution. Reasons for increase in molar conductance for the weak and strong electrolytes, that was the other point we have been seeing. That is, for weak electrolytes we had 2 points, that is number of ions are increasing because as we add more and more of the solvent, more and more of the electrolyte get dissociated. So, number of ions are increasing. Second point is, as dilution goes on, the number of ions move apart and interionic attraction decreases. So, we have 2 factors for weak electrolytes, and in the case of strong electrolytes, since they are completely ionized, number of ions are not increasing, and here the only factor is decrease in interionic attraction due to dilution. Next is degree of dissociation or ionization, and that we can say only in the case of a weak electrolyte, because alpha, that is the degree of dissociation, is equal to the molar conductance at a particular concentration measured divided by molar conductance at infinite dilution. Thank you.